So we've done the astronomy section. Now we've done the ocean section. We're now moving toward the river section. Before sort of the transition between oceans and rivers, though, I want to talk to you about volcanoes. It is the second type of mountain. First type of mountain, fold mountains, where continents collide. Second type of mountains, volcanic mountains, where material comes from the interior to the surface. All right. Molten rock inside of the earth is called magma. And when it reaches the surface of the earth, it's exactly the same material, but it has a different name. They call it lava. So have you ever wondered what the difference is? Magma and lava, just whether it's below the surface or at the surface. And when it reaches the surface, it piles up into very large piles of material that can reach above the snow line and essentially are very beautiful conical shaped mountains, volcanic mountains or volcanoes. The anatomy is quite complex. You spend a lot of time studying it. Matter of fact, the scientists that study volcanoes are called volcanologists. However, for our purposes, we're going to simplify the anatomy of a volcano into four parts, four basic parts. First of all, you have the magma chamber, which is this large, vast quantity of molten rock right below the surface. Its source was much deeper in the earth. Now it's stopped near the surface. One of the reasons it stops right below the surface is because of pressure changes inside of the earth. As it moves from deep in the earth under high pressure and gets closer to the surface, the pressure drops to low pressure simply because of the weight of rock that's on top of it. And whenever the magma engages this low pressure zone, the volatiles, the liquids and gases that it contains inside of the magma begin to be expelled. It's the same process as whenever you open a soda and you pull the tab on a soda, you hear all that hissing sound. The reason it's hissing is because when you pull the tab, you're causing the soda to go from a high pressure to a low pressure situation. And when it goes to a low pressure situation, the liquid releases the CO2, and that CO2 builds up and comes out, creating the hiss. Magma does the same thing. As it gets close to the surface, it's going to a low pressure. You're taking the lid off, so to speak, and all the gases begin to come out, and it causes it to become extremely thick, and it slows down like a slug and stops right below the surface in what's called the magma chamber. There's generally some kind of fracture above it that connects to the surface. That's called the pipe or the neck of the volcano. So we have the magma chamber below, then the pipe or the neck. And then as the material comes out at the surface, it creates a pile of material called the cone. And then the feature where the pipe exits at the top of the cone is called the crater. Okay, so what are the four parts of a volcano? Magma chamber, pipe, cone, and crater. The magma chamber, the pipe, and the cone are all distinct features of the volcano. The crater is just where the pipe reaches the surface. If the crater is more than 1 kilometer in diameter, they have another term for it. They call it a caldera. But you may see caldera. Craters are more common terms used. There are intrusions that occur around the edge of the magma chamber. If they're horizontal, they're called sills. If they're vertical, they're called dikes. And during the erosional phase, you can see those that are exposed. For our intents and purposes, we'll narrow it down to four parts: magma chamber, pipe, cone, and crater. And we'll be using these terms all through our discussion. All right, this is Shiprock in New Mexico. It helps us understand volcanoes because you're looking essentially at a dissected volcano. In other words, the erosion has removed the cone, and we're actually looking at the pipe and these radiating dikes around the edge of the volcano. So that's the pipe that's now eroding at the surface. And this is one of those vertical intrusions. Shiprock. In the dike, you can even see as the fracture opens up, you can see what they call the sheeted dike complex, the different layers, It's like we saw on the ocean floor. Difference is this is solid lava or solid lava rock rather than pillow lavas because it didn't form below the sea. But you can see the same process. All right, the types of volcanoes are defined by the shapes of their cones. By far, the two most common are the composite volcano, which you see here, what we normally think of when you think of a volcano, composite volcano, and a shield volcano. Shield volcanoes are very low angle. The reason they call them a shield is because it looks like a shield, a warrior shield that's been laid on the ground, very low slopes. We normally don't think of shield volcanoes when you hear the term. We think of composite volcanoes. And the main difference between those two is simply the composition of the magma. If the magma has a low silica content, it's very fluid, it flows over a long distance and creates a very low angle cone. If it's high in silica, it's very viscous, it's thick, and so it piles up and forms a steeper cone. Even though they're quite rare, thank goodness, there is another type of volcano called a caldera volcano, and that's where the whole top of the volcano has collapsed into the magma chamber. They are quite rare. However, we do have a gigantic caldera volcano that is still active right in the middle of the United States. They call it Yellowstone. The hot springs and the geysers and everything of Yellowstone are because of this caldera.
On the hotspot. So it's making.
We're going to begin looking at shield volcanoes first, and then we'll, after that, we'll talk about composite volcanoes. Most of the shield volcanoes occur on the ocean floor because the material coming up through the ocean floor is very low in silica. And because they're on the ocean floor and the ocean floor is moving very often, it will form chains of shield volcanoes. The most famous, of course, is the Hawaiian volcanic chain. That's what's being described here in this GIF. Or this video.
When the plate is moving on the hotspot, so it's making a chain of volcanoes, a chain of islands.
So the plume of material inside of the Earth is called a hotspot. And as the plate moves over it, it burns a series of holes, a series of volcanoes. You can see it here, how they form. And the chain continues, not just what you see above the water. If you look at the Hawaiian volcanoes, there's also a chain below the water as it continues to the northwest as the Emperor Seamounts. Yeah, I forgot I have the Google Earth. This is the Hawaiian chain here. And you can see the Emperor Seamounts below the surface. You can even trace it up to Midway Island and you can see the, is that right? No, I'm sorry. Hawaiian. I think these are the Hawaiian seamounts and those are the Emperor seamounts. But you can see how it shifts directions because the plate angle changed. The direction it was moving. But with Google Earth, I can take you down to the main island of Hawaii and show you the main volcano there called Kilauea. We can even go down into the crater of Kilauea and see the fissure eruption and the lava flows that have come out. These are active volcanoes. They still erupting. I think the last major eruption was in the 80s or 90s. There have been subsequent eruptions since that. This is looking at the main island of Hawaii from one of the other or the edge of the island, and you can see the shield shape, the very low angle. Why is it a low angle? Because the magma is low in silica, therefore very fluid. When it comes out at the summit, it flows over a very large distance, creating a low angle slope. As the volcano moves off of the hot spot, as the plate moves, it's no longer being supplied with material, and so the ocean begins to cut away at the volcano And it begins to cool. And when things cool, they contract. And so they begin to sink deeper and deeper into the ocean till eventually you can't see them at the surface anymore. However, the remnants are still there below the surface as seamounts. Because shield volcanoes have low silica and they're very fluid, they release their gases quite rapidly. And so they don't build up. So shield volcanic eruptions are really quite mild compared to composite volcanoes. However, they do have some what they call pyroclastics, ash clouds that form. That's what you're looking at here is an aerial shot of an eruption of Kilauea. You can see the lava flowing down to the sea below, but you can see the ash that's rising, fragments of the volcano that's been pulverized. And the warm air, the hot air is moving them upward. This is called pyroclastic. Pyro in Latin means fire, as in pyromaniac, and clast means to break. So pyroclastic means fire broken, essentially. The eruption of the volcano has broken the rock into tiny fragments and they're rising as ash, pyroclastics. As I mentioned, the eruptions of Kilauea are quite mild, so it has a parking lot here, so people would come and watch it erupt. It's on the high side of the fire pit, as they call it. So when it does overflow, it flows in the opposite direction, not over the cars in the parking lot. However, during an eruption phase, you wouldn't be parked in the parking lot. It'd be way too hot just to be in the area. They call this the Hale Mau Mau in Hawaiian, because we're in Hawaii, we're going to be hearing a lot of Polynesian names that they're pulling out of the language for these features. This is the Hale Mau Mau. Had a student many years ago. His name was Satoa Fiatiti from Hawaii. Sat right where Anna's sitting now, front of the class. And whenever I said Hale Mau Mau, he kind of laughed because he's from Hawaii, and you have to pronounce it like the Hawaiian. So he trained me to say it the right way, but I don't like saying it because it makes me sound too Polynesian. But the correct pronunciation would be Hale Mau Mau. Okay, so the Hale Mau Mau, the fire pit, is the English translation. They call it the fire pit because just below the surface, about 3 feet or so, is molten rock. So if you're going to walk out on that, you need to put on your asbestos flip-flops because it's going to be really, really hot. During eruptive phases, the crust of the Hale Mau Mau breaks up. And you can see molten rock rising to the surface and eventually fills it into a pool of lava and rises above the edge of the fire pit and flows out as a lava flow. You can see the glass crystals forming on the surface, and they interweave and mesh together eventually to form a thick coating on the surface. And then inside is still molten. And eventually that molten rock will break through and form another lobe. The surface can be very smooth, or it can look like coils of rope. Geologists have given this type of lava flow the name pahoihoi. Okay, and there are 2 types of pahoihoi. There's smooth pahoihoi, which you see here, and there's ropey, which looks like coils of rope. In this case, you can see smooth pahoihoi here and ropey forming there. So they're very, it's just a textural difference, I guess. Here's a geologist trying to take a sample. It's very difficult. I mean, you're dealing with rocks that are over 1,000 degrees Fahrenheit. So it's very difficult to get close without, you can do it, but just for a short while. You couldn't stay near the lava flow for a long time. This is a ropey pahoihoi. You can still, it's in the process of forming. Whenever that crust forms on the surface over a long time, it can actually create a tube or a tunnel. It's one of the hazards of being out on one of these volcanoes is you could be walking across the surface and not realize that below your feet, there's a river of molten rock. You can see a hole there looking down into the lava flow. So if that were to give way, then you would be swimming in molten rock, which is not a very pleasant thought. So it's always best if you're hiking a volcano to make sure you have a geologist with you to know where the lava flows are. A lava tube. You see?
Kilauea's craggy surface hides a network of natural tunnels, an underground system through which lava travels in enormous quantities. When the passages back up, melted rock spills onto the volcano slopes.
Then you know that lava is moving very fast under in lava tubes, lava tunnels.
After the lava passes by, you can still see the remnants of the frozen lava flow. The first type of lava flow is called pahoehoe, where you have a smooth surface or a ropey surface, and the lava flow travels quite rapidly. It could travel at several feet per second, what we normally think of. However, there's a second type, not quite as photogenic, called aa flow. It's spelled A, capital A, little a, aa. Polynesians really love their vowels, I guess. And an aa flow just looks like a big pile of rock, essentially. And you don't even know it's moving. Every few hours or so, there may be a cascade of material down the front of it, and then it stops and appears not to be moving. However, it is creeping along like a giant slug, the speed of the hour hand on the clock, and it's carrying these blocks of rock on its back, piggyback style. So pahoehoe flows are quite rapid, feet per second. Aa flow, feet per hour or more, and so on. I'm not going to show you a whole lot of aa flows because they're really boring. It's just a pile of rocks. I showed you this one because you can actually see the molten core a little bit along the edges. All right, there is another type of volcano called a fissure volcano. You can find them in isolation. However, fissure volcanoes very often occur with shield volcanoes, especially along the outer edges. This is a photograph of a fissure eruption. This isn't in Hawaii, though. This is a Snake River plain, but you can see the fracture here, and you can see the lava just flowing out of it like a wound. This is what the fissure volcano looks like in Iceland. You can see the fracture. You see how the lava has just flowed out on either side. When you have fissure eruptions, it's only a matter of time as it erupts, then it gets clogged. And as a fissure gets clogged, it forces all of its energy into one section of the fissure and can create a giant fountain of lava that can shoot hundreds of feet into the air, which are quite spectacular. The fountaining phase of a fissure eruption. Anyway, this is another shot of a fissure vent. I think this is from Hawaii, this particular one. Whenever you have lava flows that spread out from, especially from fissure eruptions, but other volcanoes, the lava begins to cool and crystallize, especially deep inside the lava flow. It forms a very particular jointing pattern or breaking pattern called columnar joining. And so you see these beautiful structures, they almost look man-made, but they're not man-made, they're natural. It's a natural feature of the cooling of a lava flow. And when you find these columnar joints, they can tell us a lot about the area. First of all, there was a lava flow here at one time. We can also see the cooling direction. The lines of the columnar joining are along the lines of the flow of the heat through the rock, which makes sense. It would be a vertical flow from the bottom of the lava flow to the top. And most columnar joinings are vertical. However, there are places where they bend, you see here. And we see that bending effect. That means there were localized changes in how the temperature was distributed. Anyway, these are photographs taken of columnar joints in different parts of the earth. Here you can see a very good example of where you had a local heat source or something that causes the bending in the columns. At the surface of the columnar joints, it looks almost like a paving stones you put down. The most famous of all the columnar joints, though, are Devil's Tower, especially you see in the movie Close Encounters of the Third Kind. They make a big deal about Devil's Tower. It's the neck of a volcano. The magma was trapped inside of the neck, and when it crystallized into these columnar joints. And the cone has long since been eroded away, and the surface is cut down to the neck of the volcano, which is exposed. The way that shield volcanoes grow is by lava flows that extend the volcano out as they flow all the way to the ocean. However, there are parasitic cones that can form along the edge, and they also cause the volcano to increase. The image above is before, and the bottom image is after. And so you can see this particular cone here is right there. And it erupted, but there was another cone that formed here, which would be about here in the before. And you can see how much of the island was added. This is a community here. See the streets. And so that's probably a good, 2 or 3 square miles of material that was added to the volcano in one eruption. So there's a battle that's going on between the volcano that's growing upward and outward and the ocean that's trying to erode the volcano. As the lava flows toward the sea, eventually it reaches the coast. And so you have fire and water impinging upon each other. And the water flows over the lava flow and causes it to harden into glass. And the island grows larger when it's active. Wait, just some photographs of lava flows reaching the ocean and the steam that's produced.
A goddess of the sea presented her, each Helens fire. Through the terrible death, the death, fire, and water. Helens, and the goddess of the sea. But the spirit was still very much alive.
The image I wanted to show you for the images of the video of the waves and the lava flow interacting. However, the storyline from the documentary is important too, that within Polynesian mythology, they've actually incorporated this element of geology and the battle of two sisters, a cat fight, I guess you would say, between two sisters, the volcano being the older sister and the younger sister. Is that right? Or the ocean's older? I can't remember which one's older or younger, but they're fighting it out. Diamond Head, Hawaii. It's an older parasitic volcano. It's being cut into the edge, or the ocean is cutting into the edge. They call it Diamond Head. There's actually a large Hawaiian community there called Diamond Head. You can see how close the hotels are to the beach. And you ask the question, why in the world did they build such a large structure right at the beach? And the answer is they didn't. They built it far from the beach. The reason it's so close to the beach now is because this whole area is sinking, it's subsiding, and the ocean is encroaching. And what that's telling geologists is the main island, Hawaii, has moved off of the hotspot. And so it's no longer growing, it's cooling, and therefore contracting, and therefore sinking into the sea. There is a new volcano that's formed on the sea floor. I think they call it Luiki. Can't remember the name, but it's below the ocean, but they believe that will be the next island in the island chain. And so many of the parasitic cones are actually out in the ocean now, and the ocean is having its way with them, dissecting it. You can see the layers of the lava flow from the carving of the ocean there, showing the internal layering. It's kind of cool. This is an image just showing, when you look at the Hawaiian Islands, you're actually looking at the very summit of a very large volcano that's building up on the ocean floor. As the shield volcanoes sink into the ocean in the more tropical areas, they form reefs, these growing boundaries around the edges. And as the volcano goes below the surface, the reef continues to grow upward because it's alive, essentially. And the reef is growing faster than the island sinking, so it can keep up with the sinking. And it creates a series of circular reefs called atolls, A-T-O-L-L-S, atoll. And it's the remnants of these old volcanic chains. It only occurs in the tropics where you can have reef formation. But in a few cases, you can still see the old volcano around the, or in the middle of the reef system. All right, any questions on shield volcanoes? The reason the shield volcanoes look like shields is because the magma is low in silica, therefore it's very fluid. It flows over a long distance. Since it's fluid, the gases can escape quite rapidly. And so there's not major massive destructive eruptions with shield volcanoes. Now we're going to talk about composite volcanoes. They're different. They are extremely dangerous and volatile. They have lots of pyroclastics to go with the lava flows. That's one of the reasons they're called composite volcanoes, or sometimes referred to as strata cones, because they're made up of two different layers, a composite of two layers. First the lava flow, and then first the pyroclastics and a lava flow on top of that. And the reason it's so eruptive is because it has high silica. High silica means it's very viscous, therefore it traps the gas, builds up to critical pressures, and then it explodes, creating a tremendous amount of damage and pyroclastics. To illustrate, I always think about when I was a child and we would go to a cafeteria and I would get a Coke and a straw, and I'm like 7. And so I'm blowing on the straw and creating bubbles. And it's really cool because it like tickles my nose at the top. And my parents would say, stop that. That's annoying. People are watching, things like that. And I'd stop for a while and then I'd do it when they weren't looking. And so one time my mom bought me a malt, not a shake, but a malt, which is very thick. And I thought, well, I'll blow some bubbles. So I blew on the straw. Nothing happened. So I blew on the straw again and nothing happened. And I was just about to blow on the straw the third time and something happened. The gas that had been trapped in the bottom of my malt because it was so thick exploded, and it went all over my face. It went all over my mom's hair. It actually went over my head to the people in the booth behind us and got all over their stuff. It was a volcanic eruption of malt. And it's the same process. It built up that gas pressure until it was catastrophic when it was finally released. So it's the thickness of the magma, which is controlled by the silica content. Higher silica, thicker magma, more gas, more rapid explosions, and therefore more pyroclastics, and creating a strata cone. Not just lava with little pyroclastics, but lava with a lot of pyroclastics and so on. The most famous of all the strata cones is Mount St. Helens, and that erupted in 1980. And we're going to go there and spend quite a bit of time looking at it, try to understand it. But I wanted to just show you some other strata cones around the world first. This is one of the most symmetrical of all volcanoes. It's Mount Fuji from above. Composite volcanoes tend to be very symmetrical with steep slopes. Why are the slopes steep? Because the magma is thick. When it comes out, it stays close to the vent. Yeah, I think is this Fuji? Yeah. That's Mount Fuji. You probably heard of Mount Fuji. I always can remember the height of Mount Fuji, 12,365 feet. Because there's 12 months in a year and 365 days in a year. 12,365 feet. You see the beautiful symmetry of the strata cones. Oftentimes during eruptions, because you have movements in the air masses, you can create, and you have a lot of electricity, static electricity from the pyroclastics, you can create extremely beautiful lightning shows. Anyway, strata cones, Indonesia, you see the pyroclastics rising. This is Mount Etna in Sicily. See the plume there of, this is Sicily. Mount Etna, very large volcano in the pyroclastics. I think it was erupting in the 90s, causing all kinds of consternation. These are images of Mount Etna at different stages of its eruption with its plumes of pyroclastics. They can be quite massive, especially after the main eruption or during the main eruption. Looks like a cloud, but it's not. It's pyroclastics from a volcanic eruption. All through Central America, Mexico has its volcanoes, Cascade Range in Washington, Oregon, and Northern California. This is the Yucatan weather satellite. You can see the initial plume of El Chichon. That's 1982. A few hours later, it's covering pretty much all of the Yucatan. And that's a thick plume of pyroclastics. What that means is the people below that are experiencing night, but it's in the daytime. It's very, very dark. This is a photograph taken of the initial plume of Chichon, and before and after. So it literally blew its top, blew the top off of the volcano. This is a nearby village. You can see the cement wall and the 1-inch rebar. Which way would you go to get the volcano, left or right? You see what it did to the bar? It bent it. The winds actually bent the bars. And so you would go to the right to get to the volcano. This is what they call flagging. So it shows the intensity of these types of stratocone eruptions. It's a photograph taken at 1 p.m. near San Cristobal, I think is the city. The dots you see there are not snow, that's ash that's falling on the city. Because volcanoes rise above the snow line, there are snowpacks and glaciers that form on the summit. And so as the volcano begins to erupt, they will melt the snow. And the melting snow mixes with the volcanic material during the eruption, and it creates a very, very thick fluid flood called a lahar. A lahar is a volcanic mud flow. And because the material is saturated in pyroclastics, extremely dense, like chocolate milk, like thick chocolate milk. And so when it flows through an area, it can pick up buildings and rip them off their foundations, which you see here in from the old Chichon. Chichon also had a lahar with it. This is a video clip that shows the lahar associated with Mount St. Helens eruption.
Clogged rivers went wild. Thousands of fish died. Some in waters heated to 100 degrees Fahrenheit. In the words of the prophet Isaiah, I will lay waste to mountains and hills and dry up all the herbage. I will turn rivers into islands.
That's an interesting connection of scripture. I will turn rivers into islands, because that's exactly what a lahar does, is that it flows, it's very, very thick. It flows into the river valleys and it stops. It leaves all the material there. And so what once was a low area becomes a high area. And so whenever there are rains, subsequent rains, they don't flow through the valley system. The valley systems have all been clogged. So it flows out over people's land and floods them. And so people that have experienced lahars during the rainy season, they have to put up with probably 4 or 5 months of being submerged underwater, and they have to learn how to live in a different environment because the rivers are now islands, as Isaiah said. So what we're going to do today is we're going to look at some of the composite stratovolcanoes. We began last time, but I want to get into a little bit more detail and also take you to Mount St. Helens and the along the Cascade Range, western coast of the U.S., and talk about the eruption in 1980, which is a great laboratory for studying composite volcanoes. Okay, one of the features of a composite volcano or a stratocone is called a nuée ardente, which is French, which means a glowing cloud. Nuée meaning cloud, and ardent meaning glowing or fiery. You've probably heard the term in English, ardent. They have an ardent love, a fiery, a hot love for someone. That comes from the French, ardent, which means fiery. So nuée ardente means a fiery cloud. And it doesn't look fiery during the daytime. You can see it coming down the slopes here of the volcano. See that cloud racing down the slopes? Nuée ardente. At nighttime, though, you can see the incandescent glass fragments in it, and it glows. It looks like a layer of a river of blood coming down the volcano at night. During initial eruption of a composite or a stratocone, you have these nuée ardentes that go all the way around the volcano, sometimes called the halo of death, that's coming down the slopes. The problem is you really can't see the individual clouds, the individual currents during massive initial eruptions. And so most of the time, when you see these images of a nuée ardente, it's after the major eruption. This is a minor eruption afterwards, but you see this current of cloud here. You see one there. You can see one here. You can also see the vertical blast of the pyroclastics rising vertically. The difference is that the cloud that's hugging the ground there is very, very dense. It's the air is dense because it's saturated with very, very hot gases and tiny, sharp fragments of glass that have been heated up to a point where they begin to glow. They give off light. Whenever the initial mass of air comes out of the crater, it traps a layer of air underneath it. So it's a very massive, thick layer of air with a clean layer of air underneath it. It forms a boundary. It would be similar to whenever you throw a playing card across a glass tabletop, you know how fast it moves? And the reason it moves so fast is because that card has trapped a thin layer of air underneath it. And so it's acting like a hovercraft. It's being suspended above the table. And so any initial movement or any angle will cause it to increase in velocity. The exact same thing happens at the summit of the volcano when this mass of thick, dense air comes out of the volcano. It traps a thin layer of air underneath it that acts like a cushion. It buoys it up, and so it reduces any friction. And as this massive air begins to move down the slope, which is a very steep slope, it gains higher and higher velocities. By the time it reaches the bottom of the slope, they estimate that these air masses can reach velocities of 150 to 200 miles an hour. So what that means is that you have a 200-mile-an-hour wind, like we saw in the tornadoes. The difference is that this wind is not nice, clean air, but it's saturated in glass shards. If a student asks me, what is the most terrifying natural phenomenon in terms of its sheer destructive power? Nuée ardente. Because whenever this 200-mile-an-hour wind full of sharp glass hits a community, it just rips everything off. If you're standing out in it, you would become a skeleton. It would rip all of your skin and all your muscle tissue off. And when they go into villages that have been hit by nuée ardentes, oftentimes that's what they find. They find denuded skeletons because all the flesh has been completely ripped from their bodies. Since it's moving so quickly, it can damage areas very rapidly. They estimate close to 10 to 20,000 people can die within a minute or two as these massive clouds move through a community. Anyway, that's another example of a noir d'onde, just this very rapid flowing mass of hot glass coming down from the summit. You see it here? This is a photograph that was taken of an approaching noir d'onde. So we're looking into it as it comes down off of the volcano. Here's another photograph. Later, we'll be looking some videos and I'll point out the noir d'onde in video form. This is in the Philippines, showing a couple of noir d'ondes coming down the slope. In the Virgin Islands, there is a volcano there, Mount Pelée, I think is the name of the volcano. And on the island of Saint Martinique, there was a town there, I think they estimated about 20,000 people, called Saint Pierre. And this is a photograph that was taken of the town after the noir d'onde went through. I've seen estimates as high as 30,000, 20,000 to 30,000 people died within a matter of minutes. So you can see it just completely ripped up all the, I mean, it's essentially a tornado, a very thick tornado. So it ripped all the buildings away. Out of 20, 30,000 people, I think there were 3 survivors and 2 of them were underground. One was in a dungeon, one was in a basement. The third was in the lower floor and they survived, but not without tremendous scarring. So yeah, most deadly, most frightening natural phenomenon in terms of its aftermath, probably a noir d'onde. The destruction is very intense, very localized. This is there's a movie called Dante's Peak with Pierce Brosnan. And it's a good movie to watch if you want to see all the different ways you can die in a volcano, because he's like traveling through during the volcano and everybody's dying around him. But this particular scene shows a noir d'onde. I think in the movie they call it a pyroclastic flow. And I don't think that's the most common term for it. Pyroclastic flows are a little bit different. Doesn't have the heat involved and the glass involved. But I think they do show, they do a good job, I think, of showing the power of a noir d'onde, how fast they move and what they do to buildings when they hit them. So anyway, this is from Dante's Peak. Give me just a second. I need to turn on the sound sharing for the Zoom. So that's the vertical blast, the initial blast. All right, you see the cloud here coming over the ridge? That's the noir d'onde. This is the vertical blast. You can see big chunks of rock coming out. They call those bombs.
Oh, what is that? Mom! What is that? That's a pyroclastic cloud.
Yeah, no, it's not called, sometimes they call it a pyroclastic flow, but that doesn't involve the temperature. The pyroclastic cloud would be the pyroclast going up. What's coming toward them is a noir d'onde, because the way it rips everything apart. Yeah, I'm trying to find the bombs.
Mom, it's coming!
You see the red in there? That's what would make it a noir d'onde rather than a pyroclastic flow. Certainly not a pyroclastic cloud, because that's going vertically. Sorry about the definitions. The definitions are important, that you define things correctly. So, the only way they're going to survive this is if they can find a way to get below ground.
Look back, kids. Don't look back.
Yeah, these are the bombs you see in front, just big chunks of rock that have been blown out of the crater.
Oh my God.
That's the pyroclastic cloud. So they survived because they ran into an old mine shaft and it collapsed behind them, so they did get underground. All right, this is a satellite image of the Cascade Range. It's formed, the volcanoes of the range are formed as the Juan de Fuca plate, and the Pacific is being subducted underneath the North American plate. You see the white dots there? Those white dots, each of those is a volcano. That's the snow caps. It's the volcano rises above the snow line. And some of the volcanoes in the Cascade Range are, of course, Mount St. Helens, which we'll look at, but also Mount Rainier and Mount Hood, Mount Shasta, and so on. All right, so at Google Earth, I can take you down to Oregon, Washington, Northern California, and you can see the Cascades here. And you can see what's left of Mount St. Helens after its eruption. Most volcanic eruptions are vertical. Everything goes straight up. As you can see with Mount St. Helens, most of the material is ejected northward along the ground. They call that a lateral eruption. And so you can see the amount of damage to the north compared to the damage to the south. So with Google Earth, I can take you down into what's left of the summit. And right in the middle is what they call the lava dome, which is like a cork that's been injected into the neck. And it's holding the pressure in the magma chamber to keep it from erupting again. If we look to the north, you can see the tremendous destruction that was created by the lateral blast. I think the evacuated area around the volcano before it erupted was 8 miles, something like that. And I think the destruction to the north was something like 13 to 15 miles. There's also a lake there, which is your Spirit Lake. So the blast was directed almost directly at Spirit Lake. I think that may be Mount Hood in the distance. It's a photograph taken of Mount St. Helens before it erupted in 1980. You can see a bulge forming here on the northern flank. That's called the Goat Rock. And there had been previous minor eruptions from the Goat Rock. In the foreground, you can see Spirit Lake. It's a little bit closer view of the Goat Rock here. And you can even see a lava flow from the 1800s that came from the Goat Rock and took out a major section of the forest there. So they knew that Mount St. Helens was an active volcano. And they were watching it very closely in the spring of 1980. Is that right? Yeah, probably late winter, early spring, it began to blow up like a balloon. You can see it here because the magma wants to get out, essentially. Whenever they began measuring this rapid bulging in the northern flank, that's when the USGS went in and they evacuated everybody from the area except for the people who were watching over some of the lumber industry, the forest roads and so on, and also any other American citizen who didn't want to leave, owned property and didn't want to leave, because we're a free country. And so a volcano could be growing right over top of your house. And if you don't want to leave, if you want to stay there and die, you have the right to do that in America. And there was a man that did that. His name was Harry Truman, not the old Harry Truman. There were the famous Harry Truman, just another guy named Harry Truman that had a house right down here, the base of the mountain, right underneath the Goat Rock. He was like 80 years old, and he said, I've lived here all my life, I'm going to stay. And he stayed, and now he's under about 200 or 300 feet of pyroclastic debris. Anyway, it just shows how rapidly the northern flank is growing. You could even see the fractures forming in the summit along the snow caps, and also the snow was beginning to melt. This photograph was taken at the very moment the eruption occurred. The fracture you see there is actually the beginning of a landslide. One of the largest landslides ever videotaped, which you see here. You can even see the crater as it's moving down the side of the mountain. The people in the prop plane that took this photograph just happened to be going in the direction opposite the blast. If they had been turned around 180 degrees, they would have died, but they were able to escape the initial blast. All right, this is the vertical blast here that happened just a few seconds later. You can see the beginning of the lateral blast. The initial phase of the eruption was the landslide that you see here. Released the pressure, and material began moving upward and outward. A series of images. The left-hand side shows the Goat Rock and how the neck is sort of coming out the side of the volcano. And then the right-hand side shows the progression of images. First, the landslide, see it here, and the initial vertical blast, and then the whole northern flank is blasted out laterally. This is a photograph taken by someone, a journalist that snuck in. He's to the northwestern flank, I think. You can see the vertical blast and the beginning here of the lateral eruption. And if you look carefully, you can see the Nuit Ardente that's coming over the ridge and over the trees. That's that cloud front. It's wiping out the forest in the foreground, and this is the last image that you could see anything. Evidently, he took several more photographs. He hit the automatic rewind on his camera. He threw it in the back seat, sat in the front seat, and that's whenever the Nuit Ardente hit that essentially fried him to death inside of his truck, and then buried him in ash. And they were able to dig out his truck and process the images. And those are the last images he would take, showing the halo of death coming over the trees toward him. It's a photograph taken from Mount Adams to the south. And another volcano, a man and his wife were hiking the summit. And they took this photograph right when the eruption occurred. A few seconds later, the halo of death, the Nuit Ardente, is completely surrounding the volcano. You see the woman in the foreground fell down. She didn't fall down from the blast. She fell down because she was looking at a mountain in binoculars, and then it just suddenly disappeared. She sort of lost her bearings, wondering what happened. All right, the vertical blast, gigantic pyroclastic cloud rising from the volcano, the Nuit Ardente, the halo of death surrounding in all directions. Once the ash reaches a certain altitude, it's carried by the winds. When we were looking at clouds, we talked about this type of cloud called mammatus. The difference is that's not water droplets, that's small pieces of rock. that's forming the ash cloud. All right, let's talk a little bit about the devastation to the north. This is before and this is after. So the lateral blast took all of these trees, you know, they're 3 or 4 feet in diameter, very large trees. The blast ripped up all these trees and the dirt and carried it into the to Spirit Lake and buried Spirit Lake under about 6 to 7 feet of ash. So you can see the logs there, that's from the trees that were once on the slope. And then the ash came down on top and was buoyed by the forest there like a raft. And then over the next few months, the logs begin to waterlog and sink to the bottom of the lake. As that happened, the ash also settled to the bottom of the lake. And about a year later, this is what it looks like. So the summit was here. All of this material was blown away. That's the lava dome, the cork inside, and you can see it's still an active volcano. So every few years, there's outgassing that occurs, releasing pressure from the magma chamber. This is before. The red there represents the forest. It's infrared. See Spirit Lake. This is after. The area is recovering now. Plants are beginning to grow in the area, trees beginning to grow. To the north, well, right at the volcano, the trees are completely ripped out of the ground, and the ground was ripped up. If you go out about 5 miles or so, you can see that the trees have been ripped out of the ground, but they're just rolled around like toothpicks. Then once you get about 10 to 13, 14 miles away, the trees have been combed over like you've taken a brush and just combed them. Yeah, I think the maximum damage to the north is about 19 miles. So you're probably about the 19-mile level here. We could begin to see the end of the damage. This is a ground level shot of those trees, just to give you an idea of scale, because when you look at them, you think they're small saplings. They're not. You see the people there? So these trees are probably what, 3-4 feet in diameter. So those are big trees. In the foreground, looks like a river. It's actually a lahar that's frozen in place. I think that's where we ended last time, if I remember right. The term lahar means a volcanic mud flow. And so as the volcano erupts, all of the glacial ice and the snow on the summit, along with what they call juvenile water that's coming out of the magma itself, mixes with ash and dirt and forms a very, very thick substance, like really thick chocolate milk. And it's flowing down through the valleys. And because it's so thick, it actually clogs the valleys. It stops and it fills up the valleys to where what once was a river valley is now high. And so all the water flows to the side to where people have built their houses. I think it was a quote from Isaiah. He turns rivers into islands. So what once was a river valley is now an island. It's a high area. And that's what happens in a lahar. On this particular house, you can see the bathtub ring that's formed from that thick chocolate milk here. So the lahar was probably what, 12, 13 feet high on the side of this house. It's taken one side of the house and ripped it off and carried it away because the water of the lahar is so thick, it can do a tremendous amount of damage. This is the initial phase of the lava dome formation at the very middle of the volcano after it erupted. What you're looking at is the top of the neck or the pipe. Over the next few years, it would grow in size as more and more material is moving up like a giant slug up through the pipe and clogging the crater. Which is a good thing. That acts like a cork. It holds everything in. From time to time, there'll be outgassing, release of pressure along the edges of the lava dome, as you can see here. So the initial phase is just the largest blast. After that, there's subsequent eruptions, much like we saw with earthquakes. You have that initial earthquake, but then there are smaller earthquakes afterwards called aftershocks. After the pyroclastics, there are lava flows that flow out of the vent, and that's what creates the other strata of the stratovolcano, pyroclastics and lava flow. If you look carefully here on the lava dome, you can see a big chunk of rock that's coming up out of the dome right here. They think that's a piece of the vent, rock of the vent that was just ripped off, and the rising lava has carried it up to the top. All right, any questions on the eruption? So I mentioned earlier, life is returning to the desolate area, destruction zone, and eventually it will patch over and
Link. The next day.
it will patch over and new forest will grow.
Link. The next day was Sunday, May 18th.
I apologize for the cheesy music and stuff, and the synthesizer was made in the 1980s, and synthesizers were all the rage. But it will show you some of the video footage of the eruption itself.
To gather anything they'd left behind, the homeowners were to return to Spirit Lake at 10 in the morning. But at 8:32 a.m., the birds stopped singing. A quake collapses the bulging north flank. Gigantic blocks crash downward in the largest avalanche in recorded history. Pent-up pressure found release in a tremendous explosion, blasting out of the mountain at 220 miles an hour.
The cataclysmic eruption at 8:32 was totally unexpected. 3 events occurred simultaneously. A huge slide removed the bulge and sent it down the right side of the picture.
Sorry, I just have to respond. Totally unexpected? Don't think so. They had already evacuated the area. They knew, not only did they know it was going to happen, they knew it was going to happen really soon. So no, it wasn't totally unexpected. That's all propaganda.
A vertical explosion started on the top. And finally, the goat rock exploded horizontally. The slide, the vertical blast, the horizontal blast. The roar from this blast was heard all the way into Canada, nearly 200 miles away.
As massive as the Mount St. Helens eruption was, it's really quite minor compared to caldera eruptions. This is an aerial shot of an island in Indochina known as Tambora. And you can see how large the crater is. Essentially, what happens in a caldera eruption is that the summit of the volcano falls in. It's not just that summit's blown away, but the whole volcano, top of the volcano, collapses into the magma chamber. There's also a caldera eruption in the Mediterranean, the island of Santorini. This is a current day view of the giant hole left in the Mediterranean where this volcano just collapsed into the sea. I've taken that image and tried to draw the volcano on it so you can get an idea of perspective. This part of the volcano collapsed into the magma chamber. There was a large void that was created by the outflow of lava. And so the summit collapsed into it. That created such intense explosions that it pulverized the top of the volcano and sent it into the stratosphere as ash, which blew it to the east. In a caldera eruption, there's a tremendous amount of not just energy, but pyroclastics. This, if you look at Mount St. Helens here in terms of the amount of volcanic ash produced, that's Mount St. Helens, and these are caldera type eruptions. You can see the Yellowstone volcanic fields. If you've ever been to Yellowstone, you're actually inside of a caldera volcano. Actually, you're inside of an active caldera volcano, which they don't tell tourists that because they would probably run screaming. But yes, it is a giant caldera volcano. There's also one in New Mexico, an extinct one. I remember whenever I was working in Taos, this red dot here at the north, that's Taos, New Mexico. You could look to the southwest from Taos and you would see something. On the horizon, you would see something that looked like this. And it just looked like a ridge, couple of ridges. It looked like a couple of ridges on the horizon. But if you knew the geology, what this actually was a volcano. And all of that was once blown away. And that's what it left, it's just the edges on the horizon. And if you look at it from space, you can see it here. That's the gigantic caldera left as this volcano collapse. So yeah, in terms of size of the blast and of the volcanic and material produced, caldera eruptions are or the maximum amount of energy and pyroclastics, and thank goodness they are very rare.
There's a curtain of fire.
All right, I've got a series of videos I want to show you, just sort of take you into a volcanic eruption. Most of what you'll see was filmed by a husband and wife team, Maurice and Katia Kraft. And it's really cool, and not only seeing what's happening within a volcanic eruption, but also give you a little bit of sense of how volcanologists, at least these volcanologists, perceive volcanoes, because oftentimes it's very religious, surprisingly. I mean, all through history, volcanoes have been seen as somewhat religious, like where the gods are living, Mount Olympus or whatever. But you can still see it even in a modern sense.
There's a curtain of fire. Maybe, 60 to 100 foot high fountains. Just pumping away. It was bright as sunlight. It was just magnificent.
For more than 15 years, photographer Steve O'Meara has been chasing volcanoes.
Some volcanoes just speak. It booms, like cannon fire.
We're in a chopper hovering over this bubbling cauldron, this lake of lava, and I am screaming. I've never seen anything like this in my life.
Why would anyone chase something so dangerous?
Facing your own fear, I suppose. It really sometimes is like walking down a dark alley in New York City with the murderer. And the question is he going to strike?
So they understand the danger, that it's like walking with the murderer. They could kill you at any moment. So then the question is, why in the world do you do that?
And that's exactly the way it feels when you're walking with an explosive volcano.
The O'Mearas were inspired by this couple, French volcanologists Maurice and Katia Kraft.
I am never afraid, because I have seen so much eruptions in 23 years that even if I die tomorrow, I don't care.
So you can see that even though they know that it's dangerous, they don't really care. They seem to enjoy significance of walking with something that can kill you. The ironic thing is that this video was taken in Japan at Mount Unzen, and I think if I'm reading things right, that this interview took place in the morning, right at sunrise, and that afternoon, Maurice and Katia Kraft and this other volcanologist they changed positions to the other flank of Mount Unzen, and it erupted and killed them. And so you see the irony when he says, even if I died tomorrow, he didn't have a tomorrow when he said that, which he did so many dangerous things. He could have died at any time. It's just strange that he would die the very day he makes that statement.
Even if I die tomorrow, I don't care.
The Kraft's films and photographs are so incredible because they shoot closer to the action than anyone else would dare. This is Katia Kraft at an eruption in Iceland in 1984.
The Krafts are in a league by themselves, of course. I mean, they were volcanologists, so they have a greater knowledge of volcanoes than we ever will have. I think we share the same passion.
We admired them for the work they had done and for the beautiful photographs they had taken in making people aware of volcanoes.
The Kraft's remarkable film record has become invaluable to scientists.
This is a great example of an flow. And we talked about that, where you have this molten core and the rocks are being carried piggyback style. It's filmed at night, and so you can see the incandescence, you can see the glowing of it.
The Kraft's remarkable film record has become invaluable to scientists in volcanic hazard evaluation. Well, they were... The Krafts had survived many close calls by then, but this would be Harry's first.
Harry was at the observation post at Coldwater 2 right up until the end of the week.
Just hours after Harry left his post, the mountain exploded.
Those of us who were within a radius of several tens of miles from the volcano didn't hear anything. For some peculiar meteorologic reasons, there was a skip. People in Seattle, 100 miles away, heard several booms.
The man who took Harry's place in the observation trailer was killed. His body was never found.
Yes, it is dangerous, but the most dangerous place in the world is bed, because 85% people die in bed. So be careful this evening.
The Krafts...
That's the same interview. Yeah, there a Bible verse where it says something like, we shouldn't say we're going to do this, this, and this. We should say, if the Lord wills. Prime example. If the Lord wills, I die tomorrow. I get another day.
They were fearless. They thought they were immortal, which is always dangerous.
So you see how they're defining them in terms of they thought they were immortal. The question of why would they walk with something so dangerous is actually answered at the end of the interview.
And if we stay on the top of this hill, it's possible about it.
At 10 in the morning on June 3rd, the Krafts and Harry Glicken moved closer to the volcano.
It may be a different day, but he's wearing the same clothes. That's what makes me think it's the same day. They put it in the interview in this documentary. It seems like it's the same day. If he is wearing different clothes, I think, no, it must be another day.
4:10 that afternoon, Mount Unzen.
All right, so this is the pyroclastic cloud, the vertical blast, and the Nueer Dawn is here coming over the ridge.
These hot masses have started coming
That's
down
the Nueer Dawn.
the valley and simply overtopped this position where they were and killed them, and then continued on down.
It's a great video clip showing this Nueer Dawn just sliding down the slope.
Killed the media people and the taxi drivers and so forth who were there.
Both Don and I feel that if we're doing something that we love and we die doing it, then okay.
All right, so see, now he's answering the question. That you're doing something you love, and if you die doing it, that's okay.
We're losing quickly all semblance of anything greater than ourselves.
And that's the answer, I think. You've heard people say there's a God-shaped void in our life and we're restless till it's filled. the idea of the 12-step program where you find something greater in yourself, some greater power. Seems to be a human condition. Even people who don't believe in God understand that that's a part of the human condition, that we need a perception of something greater than ourselves. And so in this case, it's a volcano. So essentially, he seems to be admitting that the volcano has sort of taken the place of God and being that greater thing.
But with volcanoes, man cannot touch a volcano.
All right, so not just this documentary, but others, whenever I'm watching them, I'm trying to collect imagery to show you what volcanic eruptions are like. And it's just all this religious content in it, which is really strange.
We can discover that volcanic eruptions are more than juggernauts that menace and mesmerize. They are the upwelling builders of our planet. They are the makers of land, of worlds, and they offer us a rare glimpse into the process of creation. Just what is a volcano? A god? A devil? Or both? Volcanoes, to humankind, they are enveloped in an aura that can only be described as supernatural. They're devil mountains and holy mountains. To some, they're upthrusts of hell. To others, abodes of the gods and spirits. Volcanoes are something else to scientists. Like a tree's rings, they're a record of growth, of the Earth's growing pains.
I'm not sure if I would agree with that either. To scientists or something else. Seems like to scientists, they're pretty much gods too. So.
Of hell at the meantime. People are much more curious about hell than about paradise. So they want to see how hell is looking to know if it's worth to go in paradise, maybe. I am like a missionary. That is to say, I want also to film volcanoes, to show it to other people.
Yeah, it sounds like I'm editing there, but I'm not. That's part of the documentary where he's talking about the volcano being an image of hell and that he's a missionary spreading, I guess, the goodness of hell. Can't imagine. I mean, I could see if hell was like a giant party, but he's depicting hell the way the Bible does, like a lake of fire so I don't know, it's just really bizarre.
Terrible souvenir. This man died the 4th of April, 82. He was killed by a blast and an ash flow coming from Chichon volcano in Mexico. He received the blast just in the face.
This is so ironic. First of all, he's collected somebody's head, a skull. He's got it in his basement, his collection. That's kind of weird. But he's showing the way the skull is abraded. In other words, when the Nuer adult hit the person, it took off all the flesh and began eroding the skull itself. And he's describing his own death. That's how he's going to die, because Maurice and Kadia were killed in a Nuer adult.
That's why it's burned here. Those are the cassettes of a volcanologist of St. Helens. He was 9 kilometers from the volcano when the blast came on him and he was killed. And those are the messages of him, but they are melted. Impossible to know what are on those cassettes now. We call this an Indian hat. That is to say, when the blast of St. Helens was coming, this trunk exploded. And so it makes a very strange shape, typical of a very violent eruption.
Sometimes they were just an arm's length from the blast. It was on this trip to Indonesia that the crafts engaged in what would be regarded as their most notorious adventure.
Because chemists don't want to go on a sulfuric acid lake. And they were doing this to take a boat and to go on this lake. It's more acid than in the battery of your car.
All right, so in the crater of volcanoes and sometimes along the flanks of a volcano, you'll have bodies of water that collect, lakes. And because the magma is releasing gases, oftentimes those gases and chemicals will make their way to the bottom of the lakes. And they build up there like a giant bubble in the bottom of the lake. And they can become incorporated into the lake water, causing them to become extremely acidic. And so you can see them holding this rock in the lake water and you see it foaming away. However, both of the rocks that they show that they're putting into the lake are limestone. And limestone by its very nature will fizz in very dilute hydrochloric acid down to like 3 to 10%. It will fizz like that. So just because this rock is going crazy doesn't mean that it's dissolving it away. If they put a granite in there, it probably wouldn't do anything. They're using a specific type of rock. So that's what do they call that? They're making a show. It's infotainment. You're pretending that you're giving people the truth, but you're really just entertaining them by creating this this belief that this lake is going to dissolve your skin away if you get into it. I remember back in the 90s, I think it was, they had some kind of gas tank in a pickup truck that was known to explode whenever it was hit from behind. And so they had this news program where they were showing a pickup truck being hit from behind and the whole thing just blows up in a gigantic fiery explosion. Then they found out later that they had put some kind of bomb inside of the gas tank. Well, you see, they're trying to convince you that this gas tank will explode like that, but they put a bomb in it. And of course, the bomb's going to cause the gas tank to explode. That's sort of what they're doing here. They're putting limestone in very dilute hydrochloric acid and it's fizzing away like crazy. And so people are thinking, wow, it's eating up rocks. It would eat me up if I got into it. And I guarantee you that probably wouldn't happen. It's not that it's healthy to be in it. Matter of fact, if you got into this lake and you stayed there for several hours, you'd probably have severe burns on your skin in several hours, but you're not going to melt in a few minutes like this would suggest.
What can happen if you fall in an acid lake? You are just dissolved. It's a problem of maybe 1 hour.
Yeah, I don't think you're going to dissolve in an hour. I think an hour probably could do enough damage that it might take your life. Because that's a pretty severe burn, but it wouldn't take your life in an hour. It'd take your life like 3 days later in a burn clinic as you're trying to. And are you going to stay in a lake as your body's burning off? No, you're going to get out. As soon as you begin to hurt, you'll climb out of the lake. So it probably wouldn't happen. But yeah, it's not like in the Dante's Peak, there's a grandmother that, well, they're on a boat and they're going across the lake. And the bottom of the boat begins to corrode because of the acid lake. So the grandmother gets out and pulls the boat to shore. It's like the whole lifeboat thing. You know, if you're in a lifeboat and you only have food for 3 people and you have 4 people, you have to decide which person's going to starve to death. The ethical dilemma. That's what they set up in the movie. You've got 2 young children, 2 middle-aged adults, and you have this old woman who's like 80 years old. Well, you're solving the lifeboat problem. She's lived most of her life. And so she gets out and she pulls the boat to shore. And then when she comes out of the water, the lower part of her body's gone as if she dissolved away. No, that's not what's happening. You're not going to dissolve in an acid lake. I suppose you could have a lake that becomes so acid that it might do that, but I've never heard of one.
Put the sampling bottle in the lake of acid, and after 5 or 10 minutes, the cable was broken. But our hands also were, all the skin went away.
That's what my hands look like when I've been in the tub for like an hour. So that's not skin going away. That's just wet hands. Plus, why aren't they wearing gloves? You know, got a lot of questions here.
When the story of Kawaiijan filtered back to the scientific world, the crafts were criticized for taking an unnecessary risk. In fact, they would confront such criticism more than once in their career.
Yeah, that's what I'm thinking. Anybody that would complain about taking a raft ride across an acid lake, that's just minor compared to standing next to a volcano that's in active eruption. The guy walking along the ridge as you're seeing bombs come out, that's craziness there. This is craziness, but it's not that level of craziness. All right, before we move away from volcanoes, I wanted to talk to you about, it's not just the acidity of the lakes, but also bubbles of gas that can be trapped, maybe not even poisonous gas. Matter of fact, one of the most deadly gases that occur along volcanoes is actually CO2, which is the exact same stuff we're breathing out right now into the room. It's just that the CO2 reaches such a high concentration that it can kill. This is a lake in Cameroon in Africa, and it sits near a magma chamber, and that magma chamber is supplying CO2, carbon dioxide, to the bottom of this lake, and it builds up in the bottom like a bubble. And during the springtime, whenever it begins to warm up, the lake will actually flip over, it turns. All lakes do this. If you've, we don't really drink tap water anymore, drink bottled water, but when I was a kid and we drank tap water, I could tell whenever the lake turned over because the tap water got really nasty tasting. Because when the lake where they're getting the water turned over, all of that sediment stuff from the bottom was actually in the water. It wasn't that it would hurt you, but it did make the water taste pretty bad for about several weeks when the lake turned over. Whenever the lake turns over in these volcanic areas, that bubble of CO2 that's trapped in the bottom comes out along the shoreline. And in most cases, it's directed in all directions. And so there's not a high enough concentration to do any damage. However, there was several cases, one back in the 1990s, I think, early 1990s, when this particular lake overturned, and when the CO2 came out, the conditions were such that rather than coming out around the whole perimeter of the lake, it came out along one shoreline and was directed right at a particular community. And when that happened, it created so much CO2 that the people and the animals just died. They suffocated. This is an aerial photograph taken of a herd of cattle that just died, suffocated from the CO2. I think there were something like 5,000 to 10,000 people in this one village that died. It was a horrible accident. They didn't know what had happened. They thought it might have been some kind of chemical weapon that had been detonated. But as they studied the area, that's what they believe happened, was just this freak accident of the release of this CO2 that was built up from the volcano.